Okay, it looks like we're streaming now. If you want to take off and watch the stream and just come back, the plan is to do that group activity at 1:35. So if you have trouble viewing this Zoom, you could come back at 1:35 for the group activity and just go watch it on the live stream. The link to the live stream is in Canvas. All right, so that said, let me go to speaker view. Whoops, let me get me up there. Okay, so I want to talk about, okay, I got to leave that up there. The following items today, and we may not get through it all because of the holiday. I didn't remember that Monday was a holiday. So my plan is to go over as much of this as I can. And then if I don't get through it all, I'll make separate videos afterwards or something and send you something. Probably I think we'll get through all of this and maybe I'll send you some review items for this. I also have some old Physics 110 videos that I could show you, and I went at very slow pace for those. So if at any point you realize, man, this is killing me, you're going too fast, talk to me and I'll send you the slow-mo videos of these where I did it really slow. That said, everybody open and look for problem 1.14. I'm going to screen share it as well. Okay. So let me find it. Okay. Whoops. Sorry about that. Didn't have it up to the right page. Give me a sec. All right, there we go. So let's start with this one. The goal of this problem, I know this seems cheesy. It's just like plug in some numbers and see if you can get it right. It's making sure you can use your tools, your calculators, making sure you know what units are, numbers are, etc. Now, again, if you do not know what I'm talking about here, I can give you some videos that does this at a slower pace. And so everyone's coming to this class at a different level. Some of you had 110 and you should jump right in and do this. Those of you that had high school physics should be able to recognize most of this, but there might be some gaps. If you have trouble, send me an email or something or put it in the chat and we'll find you some helpful videos. So let's just try and do this together. Now, I'm going to leave this up on the screen while I write down the notes here. And I need to get this. Do I have all that written down somewhere? I do. So I could erase all this crap. Okay. So I'm just going to write down what we have. And if you want, you could start a piece of paper. If this is one of your required problems, hey, cool. That's a cool trick, by the way. It looks like we're going to do so many problems, but maybe a third of them we're going to do in class together. So if I accidentally do one of your required problems in class, cool, we did it. And you don't have to do it as homework. So I hope to do that frequently. If you have already aced this problem, you could just run through it really quick and do something else from the required problems list. So if you already know this problem and did it already, and you did it recently, do something else useful. Just keep Zoom on in the background. And if I say, hey, check this out, everybody, just come back in. All right. All right. And now I'm just reading what we're supposed to do. We're supposed to compute delta x. We're supposed to answer in engineering notation with appropriate prefix. If you don't know what that means, you can look in the solutions if you don't want to listen to me, or you could watch me do it live. So I'm going to go here. Whoops, stop share. Okay, so this is basically the problem, and we're supposed to figure out what delta x is. I know this is super easy, but hey, we got to start somewhere, right? Oops. There we go. Okay, so in this case, I want to plug all this stuff in. Now, hopefully you can read that. If at any time something's blurry or whatever, just give out a shout. Just tell me if you can't read, or if I forget to screen share, say, dude, just unmute. You could hit chat. You could ask me questions in the chat anytime you want. You can ask me questions by unmuting anytime you want. All right. Questions are more fun than me just droning on at screens. So, okay. In here, we see the number. Up here, we see the units. So this is a little bit small. Let me make that a little bit bigger. Meters per second squared. Meters per second. All right. And so you've got the problem on your own paper, so you could probably read it there, or you've got the PDF. So we know all we have to do is start plugging this stuff in. So let's do it. Now, when I plug it in, I'm going to remember the units. And it doesn't offend me if you want to take off or do whatever, okay? Remember, the live stream's going. Just be back here at 1:35 for this group activity. Whoops, ran out of room. Okay. I got a calculator somewhere. And so there's many different calculators you could use. Normally, the engineering exam requires a scientific calculator. For this class, it's online. Who gives a shit? Use a graphing calculator if you want. But again, you should, if you're eventually going to be an engineer, just know the engineering certification exam requires a scientific calculator. More on that some other time. Now, I know this seems cheesy, but I'd rather show you just in case. There's a couple different calculators. Let me get the other one. Here's some common calculators, scientific. You can see I'm a TI guy, I guess. Casio's totally fine. Now, when you're typing this stuff in, the main thing I'm pointing this out is I want you to learn how to use the EE button. So this one has an EE button right here. And so that's basically times 10 to the. And then this one has a, up here, you can see somewhere it's, there we go, times 10 to the X. And so I want you to make sure you get used to using that. Why? It'll just save you time. And if you get used to that, eventually you'll get used to reading a prefix. And then you say, oh, that prefix is this number. You can just hit EE that number instead of doing a lot of work on paper. So getting used to the EE button, that's what we're doing. All right, so let's go ahead and use this one. All right, and so maybe I'll check the units really quick here. Let's just punch in the numbers really quick and do that. So I got 0.5, right, times negative 1.23 EE, negative 1. And so remember, the negative and the minus sign are different on your calculators. You probably all know this. And then times 0.0987 squared. So hopefully you got this number. I'm just going to write this down here. Negative 0.000599,114. Now, we could talk about the sig figs in just a second, but first, let's get the units right. What units should be on this term? This one is meters per second squared. This is second squared. What should be left?
Meters per second.
Meters, because it's seconds squared. Do you see that? So seconds get squared as well as the number. And then did everybody get, hopefully you got that number in your calculator. All right. So I'm going to double check it really quick. Okay. Yep, I got the same number two ways. All right, so hopefully we're feeling pretty good there. So again, it's this number, or the units we get by taking these units times these units squared because they're in the square. So that's one thing I want you to watch out for. Good job. Then over here, when we do this one, I've got a seconds times meters per second. What units should we get on the second? Whoa, I wrote second squared. Shit. Sorry. That's meters. I'm just going to punch in the numbers here. So 5.85, and then the EE button. I won't always be doing this, but hitting the EE button. That means times 10 to the -3 times 0.0987. So I got plus, whoops. And this one was in meters. Meters per second times seconds cancels out. Again, if any of this is foreign to you, I do have slower motion video or slower videos to help you later. Okay, so we know how to punch these numbers in the calculator. Turns out on test day, that's not good enough. I need to know how many sig figs should be associated with this. So let's talk about sig figs briefly and remind you. How many sig figs does this number up here have, this A?
3.
3. Everything's non-zero. It's easy. 1, 2, 3. So this one has 3 sig figs. Let's do this in a different color. So I'm going to try this weird green. Does that show up? No.
No.
Let's try this one. Is that a little better?
Yeah.
Okay. So there's 1, 2, 3 sig figs. This one, 1, 2, 3 sig figs. So this one has 3 sig figs. Over here, how many does this one have?
3.
Okay. These are leading zeros, not significant. Nice job. So these, anytime you have a number with zeros in it, the sig figs are very confusing. If you need help with those rules and sig figs, it's, I think, on page 1 or 3 or something of the workbook. More on that after this problem. So that means this number also has 3 sig figs. Sorry, I'm squeezing it in there. Okay. So now, whoops. Oh, and this number has 3 sig figs. It's the same number, right? Okay. In this case, I'm multiplying 2 numbers. Does anybody remember the rule associated with multiplying numbers and sig figs? Does anyone recall?
To quote your book, the number with the crappiest number of sig figs,
Exactly. So 3 and 3 are equally crappy. 2 is crappier than 3, right? That's fewer sig figs. If you want to know something really well, you want to know lots of sig figs. So when I say crappier, that usually means smaller number of sig figs when you're multiplying. So here, if this one has 3 and this one has 3, how many do you think this one should have?
3.
3. So here's how I mark it. Are these significant?
Nope.
No. So 1, 2, 3. Shit. Drop the marker. So this is how I'm going to mark sig figs. Okay. So notice this has 3. This has 3. All I'm doing is I'm using an underline to indicate where the doubtful figure is, the number that is affected by rounding. So this is my way of saying, okay, we're off in the millionth column. Over here, 3 times 3, this should also be 3. Leading. 1, 2, 3. That's the most significant. All right. So now we're going to add these 2 numbers up. Notice, remember, this was a negative number, so this was a negative number. Go ahead and add them up. Whoops. And so answer. So on here, I'm just going to use the, whoops, sorry. I'm just going to say my previous answer and then scroll up. So I'm just hitting the up, sorry. There it is. So I hit the up arrow and hit an enter. And now I could do that. Whoa, crap. Trying to look at the screen was too much. I'm just going to type it in. It's hard when I'm, yeah. plus 0.000. That's my kids out there screaming. I don't know if you could hear them. I can. Okay, so I got equals negative 0.000021719. Now, whoops. One thing that we need to do is check the units. Because these had meters and these had meters, if I take 6 apples plus 7 apples, I end up with 13 apples. 6 meters plus 7 meters, I get 13 meters. This number of meters plus that should be some number of meters. So the units matter. We got to keep the units. Okay. Next, how many sig figs? This number had 3 and this number had 3. How many do you think this one should have?
3.
2. Addition and subtraction use different rules. What? Ah! There was the reason we were doing this problem, okay? So it turns out if you're adding and subtracting sig figs, you keep the column. Check this out. We keep the crappier column, not the number when we're adding or subtracting. So count over 1, 2, 3, 4, 5, 6. We're off in the 6th decimal place. 1, 2, 3, 4, 5, 6. We're also off in the 6th decimal place. 1, 2, 3, 4, 5, 6. We're off in the 6th decimal place, and I threw my marker somewhere. Whoops. Ah, wrong marker. This is a different red. And notice, not significant, not significant. This one only has 2. Now, if you think this is crazy, think about this. Let's say you had 50 hot dogs and you ate 49 of them. Not enough to win the hot dog competition, but close. Well, if you start with 50 and you subtract 49, you only have 1. It's very plausible to expect the number of sig figs. 50 had 2, 49 had 2, 1 only has 1. So when you add or subtract numbers, it's very common to add or lose a sig fig. Obviously, when you're adding numbers, you tend to add sig figs. When you're subtracting numbers, you tend to lose sig figs. So I'm going to pause and see if that made any sense at all. Does anybody have a question about that? Okay, cool. One last trick. If we go back and read the question, let's see if we answered it. Oh, shocking. Read the question before you move on and make sure you answered it. I know that sounds crazy, but that's physics. Write your final answer in engineering notation with appropriate prefix. Have we done that? No. This is not engineering notation. If you're not familiar with engineering notation, that's described in the workbook in one of the required problems that you don't have to write up. It's on page, sorry, I'm just looking it up really quick in case you want it. So sig figs was on page 1. Engineering notation was page 3. And there's a bunch of practice problems if you need help with that, and I can give you videos later. But so here's the short version. If you have a number in your calculator and you want to go to engineering, it's really easy if you hit the mode button. So I'm going to try and do this while showing you. Mode button, sorry, mode. And then you just go down here. Instead of floating, there's scientific if you need scientific notation. There's engineering. Sorry. So I go to there, I hit enter. Every calculator is a little different. You got to learn how to use your calculator if you're going to ace a class, right? This is that part. Now I'm going to quit to get out of here. Second, quit. Yeah, Casios look a little different. They're great calculators. I grew up on Casio too. Now notice my number disappears. So all I have to do is type answer. So answer, the answer button's down here. So I hit second answer, and then I hit enter, and it writes it in engineering notation for me. Sweet. One less thing to screw up on paper. Now, if you don't want to do that, I'm going to write that down so I don't forget. going to do some color work here. We know that there's meters. And now we know that this is 10 to the negative sixth. If you don't want to do this, you could go 1, 2, 3, 4, 5, 6. The trick with engineering is you have to go by groups of 3. So you go over 1, 2, 3, then you go over 1, 2, 3. Aha, there's the number. Now, actually, I'm going to do it like this. I'm going to underline the 1. You're going to see me do this in my solutions. Oh, shit, sorry. This glare is killing me. Hold on, let me turn a light on. Ooh, it's dark in here. Sorry about that glare. All right, so what I'm going to do is this. Sorry. Okay, I have, this red marker's dying. Well, this is what I've got right now. Oh, shit. Sorry. Go figure. There we go. Okay, so what I did is I wrote 3 sig figs. I indicated that it should be rounded to 2. And now I've got, this is an engineering notation. I've got the units. So I've got the minus sign correct. I've got the number of sig figs clearly indicated with this underbar. I've included this extra digit for reasons I don't want to go into right now. Typically, we talk about that in lab. I've indicated the engineering notation, which means times 10 to the, and something that is a power or that is a number that's divisible by 3. So it's either 10 to the 0, 3, 6, 9, 12, something like that. And I've got the units. So did we answer the question? What do you think?
No.
No. What was the other piece that we're supposed to fix?
The prefix.
The prefix. So now you go out and you say, well, wait a minute, dude. What is the prefix associated with 10 to the negative 6?
Micro.
Micro. So this is the final answer. Negative 22. Now, if you don't know how to draw a micro, just draw a letter U and then drop this down. And then we got the meters. This is the correct answer. Now, you could either do 21.7 with the underline, or you could do 22, but you could see that you guys are not dumb. You could have got this number, but it's not enough to get the number. You have to write it correctly, because the way you guys write numbers means something to other scientists and engineers. So let me catch up in the chat. Yeah, generally, well, yeah, depending on the situation, I want you to use the symbol. And I could teach you the tricks for writing those symbols, especially if you're like worried about how to write them in a computer file. I'll show you all of that shit in lab. So during lab, I'll teach you all this annoying stuff. Okay. So far, so good. Let me just check. I'm going to go to the gallery view so I could see. All right, cool. Yeah, you guys can. I love how Zoom didn't bother to put any thumbs down. So now you could only give me a thumbs up if it's making sense, or just sit there in silent misery. Great. All right. So that's our warm-up question. We got some good look at sig figs. Let's move on. I just got to keep plowing through stuff. All right. So let's go on. Oh, there is a question there. Let me see. Okay. Nice job. All right. So let's see. What was the next one I wanted to do? Let's go to 18. All right. So let's just look at 18 part A. All right. So let's just look at this one and remind you how to do, whoops. Oh, we don't need the sig figs. Sorry. Well, actually, yeah, let's do the sig figs. Anybody that wants to, go ahead and hit unmute and tell me. Let's look at this first one, A1. How many sig figs do you see in there?
2.
2. This is a leading zero, not significant. This is a trailing zero to the right of a decimal. So this has 2 sig figs. How about this one? How many sig figs in there?
3.
3. These are trailing zeros to the left of a decimal. So they're not significant. So this is 3 sig figs. So notice leading zeros are never significant. Trailing zeros can sometimes be significant. So it's the trailing zeros. So let's look at this one. Let's convert A1 to feet per hour squared and set it up. We maybe don't do the whole thing, but just look at it. All right. So let me get this written up. And again, if I'm going too fast, you do have the live stream to look at later. Okay, so you can slow it down there. 1.18. We're doing 1.18b together. Convert 0.060, what is it, millimeters per second squared to feet per hour squared. All right. Okay, and let me go to speaker view. Here we go. So that's what we're trying to do right now. Okay, so I'm going to write this out. And notice the first thing I did was I take that prefix, this means millimeters, and I rewrote it as a times 10 to the. You guys already told me this thing has 2 sig figs, so I'm going to make a note of that in case we need that. So far, so good. Now, I love to make fun of chemistry. Nothing makes me happier than teasing chemists about how crappy chemistry is. That said, we all know chemists know how to do conversions very well. So let's give them their props for that. I mean, they've got almost nothing else going for them, right? Ha ha ha. Hey, if you're a chemistry major, by the way, I actually really like chemists. So I'm just teasing, all right? That's the classic thing physicists and chemists do. So, yeah. Okay, so I need to get rid of meters and go to feet. So one thing you could do is use Google and say how many feet in a meter or whatever. Obviously, you could punch this in Google itself, but there are times I think you might need to know this old school procedure, because sometimes I make up shit that's not in Google just to see if you know how to do it. So if you're one of those students sitting there, why don't I just Google this? You're right. You should Google this. And that's what I do in the lab. But I want you to know this technique because sometimes there's weird stuff that just every once in a while isn't in Google. So let's learn it. All right. So let's do a screen share. And then where are these conversions here? I think they're on the back page. Actually, I'm going to show you this way. On the back of the workbook, I've got some important equations. So I've tried to organize this so when you take tests in this class, you might just check the back of the workbook and you could see some of these things. So I see in here, I see 12 inches in a foot, and I see 2.54 centimeters is an inch. Unless otherwise specified, these conversions have infinite sig figs. Here's one right here. Whoops. Right there. See the underbar? That means this one only has 4. But this one is actually infinitely precise, meaning it has infinite sig figs. More on that in a minute. So what I'm going to do, I totally forgot what I was doing. Well, I know this. I can go, you could do this in many different ways. I know that 1 meter is 100 centimeters. I know that 1 centimeter, or whoops. I know that 1 inch is 2.54 centimeters. All right. So notice The meters would cancel out, the centimeters would cancel out, the inches. So I'm almost to feet. I know that 12 inches makes 1 foot. Is there a smarter way to do this? Yes, Google. We discussed that. But again, the procedure is what we're trying to learn. Seconds to hours. If you look on the back, you know there's 60 seconds in a minute, and you know there's 60 minutes in an hour. But somewhere, I think I gave you the shortcut right there, 3,600 in an hour. So I know there's 3,600 seconds in 1 hour. Now, when I look at this, let's go through this carefully and see what, just think of this as being like the numerator of a fraction, and this as being the denominator of a fraction. Sometimes chemistry people call this the railroad tracks. Well, let's see what cancels. Meters cancels meters. Centimeters cancels centimeters. Inches cancel inches, and I'm left with feet. That was good. Second squared does not cancel seconds. What do I have to do? I need to square it. Now, here's the thing students forget. You don't just square the units. You have to square the units and the numbers. It's a package deal. So you have to square it on the top, and you have to square it on the bottom. And what happens is students will come in here and see this and cancel it, and then they'll cancel this. That's wrong. That's wrong. You cancel the seconds squared, right? Because the units also get squared, but the number still gets squared. Sometimes people forget to square the number, and then they miss those easy points. All right. At this point, you could punch in the numbers. Let's go ahead and finish it. I'm going to do it as well. So just practice using your calculator. 0.060 e -3 times some crap. Times 100, divide by 2.54, divide by 12, times 3,600 squared. So I got 2.5512 times 10 to the third. Now, what units are left? Feet and hours squared. Okay. How many sig figs should this have?
2.
2. Usually, not always true. Good job, Olivia, as well. Usually, but not always, the number of sig figs you start with should be the number you end with in a unit conversion, okay? So if this has 2, think about this. This technically looks like it only has 1, but because it's involved in a unit conversion, unless otherwise specified, we assume this has infinite sig figs. So a billion, a billion, a billion, a billion, a billion, a billion. So we don't think of this as having 1 sig fig or this number. They're exact calculations unless otherwise specified. So short version, usually, and I don't try to screw with you on this one, usually if you start with 2 sig figs, you should end with 2 sig figs. So then we could just get rid of that. The reason I like to hang on to the extra digit is to avoid intermediate rounding error. I'll show you an example of that in just a second. So that's that problem. That was it. So it's good to know how to use conversions. Feel free to use Google, but you still are expected to know that one. I just want to show you something really quick. Here's the deal with this. Notice in this problem, all of these numbers start with 2 sig figs. So what I'm trying to show you right now is why it's important to keep the extra digit. See what if I say keep 1 extra digit. These all have 2. So I underline this, but keep an extra digit. Okay. In this one, I didn't. I rounded every step. And look what happens at the end. If you round every time, eventually you can be off by as much as 20%. Obviously, this question was a little bit contrived, but it's very common to see students on test day round too soon, and then they end up off by 5 or 10%. And sometimes that's enough to lose points. So that's why I'm in this habit. Oops. That's why I'm in the habit of showing where you should round, but then not rounding. Because if I need to use this number for a subsequent part of a problem, I don't screw up now. And interestingly enough, if you've ever used Microsoft Excel, which we use in lab, you could choose the rounding digit, but it keeps all of the extra digits. Microsoft Excel also avoids rounding errors, which is good. Okay, more on that tomorrow in lab. I'll show you that. Okay, so there was that question. Let me pause. Any questions, anybody? Okay, just trying to do a quick review to get you up to speed. Let's look at another question. Let's go to 28 in chapter 1. Whoa. Okay, so in this case, let's look at 28 really quick. Oops, actually, let me screen share while I'm doing this so you can see. I'm going to get some notes on my page here. So we're looking at 28, okay? Those of you that had me for 110, hopefully you agree it's a little bit faster. Ooh, let's go to this marker. 1.28. Okay. Got a circular plate. You cut a hole out of it. The hole is a square. We've got these distances measured in units of D, whatever D is. D looks like it's the diameter. Okay. We're told, is this? Okay, it says the thickness of the plate is T. I'm looking at this. So that's the dimension into the page. So if I could kind of draw it like this, it's maybe some like can look, sorry, I can't draw this very well right now, but that's the thickness into the page. So that dimension into the page that I'm having trouble drawing is T. So rather than do that, let's just clear that. Let's get out of there. So it looks something like this. So we're told thickness, and that's the dimension into the page, is T. All right, that's cool. And we're told the mass is M. I'm trying to demonstrate a good problem-solving strategy. Notice what I do to do these problems. I've got the book there, but I still write everything down on my own paper because eventually these problems get so complicated. You don't want to have to keep going back and forth. So just get this stuff on your own piece of paper and start working. All right, so it says determine density. Now, in physics, we don't use the letter D for density for obvious frickin' reasons. We use D for diameter a lot. So we're going to use the symbol rho. Now, if you don't know how to draw rho, it's the Greek letter rho. It's just like a P, except you start here, go curve around and then down, curve and down. Now, it's important that you learn how to draw Greek letters correctly because later on in class, there's going to be momentum. There's going to be pressure and power. There's going to be density. So there's 3 different P's. We're going to have T. We're going to have tau. We're going to have capital T. We're going to have double strike capital T. There's going to be lots of different letters, that look the same. It's important that you learn how to write Greek letters. Enough said. If you can't do it, figure it out and I'll help you. All right. If you're bad at it, just ask me and I'll show you, right? But we'll do that in office hours. Rho your density. All right. Anybody know an equation that talks about density? Any equation, you know.
Rho equals mass over volume.
All right. So let's say rho is mass over volume. I'm using a capital M and a capital V. If you're wondering, this would be a lowercase v for me, and a capital, I put these little serif on there. Whatever. Okay. Now, if we know it's mass over volume, we know the dimensions of this thing. How could I get the volume? We know the mass is M. We got that. How do I get the volume?
Reconfigure that equation to get volume.
Well, remember, we want to determine density. How do I get volume from these dimensions? That's what I should have said. Sorry about that.
Oh, subtract the volume of a cube from a volume of a plate.
And remember, it's not a cube. It's a square with thickness T. If it was a cube, the thickness would be the same as that. You know what I'm saying?
Right.
So I guess we should technically call it a square plate or rectangular solid or what. I get the idea. So you said subtract the volume of the, how about I just do it like this? Volume of the square. Oops. Sorry, the chat there. Yeah, anything. I don't really care about that, the name of it so much. Does that make sense? Is that basic? Yeah. So give me a formula. What's the volume of the, and since you answered that, you guys, let's let somebody else get involved. Somebody else. What's the volume of this in terms of the given parameters? Or anyway, what's the volume of this circular plate?
Pi r squared times height.
Pi r squared times the height, sure. And then this one would be, whoops. The volume of the square one would be, say, side squared times the height, right? But now what we have to do is get these equations in terms of those variables. So how do you get the radius in terms of this shit?
Diameter divided by 2.
So we know that r is equal to diameter over 2. What's the height in this case?
T.
T, that's the thickness. What's the side?
D3 or D over 3.
Whoops. And so side is equal to D over 3. And I'm going to try, by the way, people, I should be better at this. I know when I can get away with it and when I can't, but if you're new, you should stop writing the diagonal fraction bar. Just start writing a horizontal one. What happens is, as the problems get longer and longer, you kind of forget what was under the fraction and what wasn't. So if you're not good at physics, which is most of you, well, basically all of you, right? You're in your first day of class. You better listen to me and do what I say. Start writing these fractions horizontally. So that way you have a higher probability of passing. Okay. All right. Oh, and the height here, isn't this also T? So now let's plug all that crap in and do algebra. Race me. Okay. See if you can get this simplified. See if you can get all those numbers. Go for it. I'm not going to think too much. I'm just going to plug it in one step at a time so I don't screw up. That's what I found is the fastest for me. You could do whatever you think is right.
Is it pi over 4 d squared minus?
Oh, so I'll cut you off there. Remember, if you're faster than me, how do you check the answers? The solutions are online. Because this is going to happen all the time where you finish faster than me. Because I got to do on the way. So does that make sense?
Yeah.
So see if you can find it. No. And that's good. Yeah. You're probably ahead of me. Sorry, I forgot a squared here. So this is going to equal pi over 4 d squared t minus 1/9 d squared t, which is, I think what you were just saying was right, but it takes me that long to get there. So again, definitely d squared t. So that looks like the volume. Now, a lot of you are used to a math class where you leave things like this with fractions, or maybe you get a common denominator or whatever. As an engineer, this sucks. Use a decimal. Plug it into your calculator, people. Pi div 4 minus 1 div 9. I'm going to write, engineers normally use 3 sig figs. So how many do you think I'm going to write? If we want 3 sig figs, how many am I going to write?
4, because you still have to do
Yes,
calculations.
exactly. So I'll just stick a couple. Now, we haven't specified this, but usually as an engineer, you have to have at least 3. No engineer wants to see 5, but I know I've got to plug that in up here. All right. And so now at this point, the rest is easy, but I'm going to show you in the solutions. All right. So, whoops, let me screen share. So here's a trick you could do with the solutions. All right. I want you to waste as little time scrolling as possible. If you hit Control F, whoops, am I in this file? Control F, you could go to find. And what problem was this? 1.28, I think. I type in the problem number and it usually gets you pretty close. All right. So there we go. And notice this was the correct way to write it. I want to point out a couple of things. 1 over this is generally speaking not acceptable, right? So it's bad form to have the fraction or the decimal number in the basement. So you just pull that part out, flip it upside down, and this is the correct way to write that. Why don't we have units though? All day I've been saying, check the units, make sure you look at the units. It's because it's an algebraic problem. If you plugged in a number for mass, it would have, say, like 0.61 kilograms. The units would be included when you plug in the units. Oh, sorry. The units would be included when you plug in the numbers. So typically, we do not include units on algebra problems. We do include units on numerical problems. Not always, there are exceptions, but by and large, that's the rule I want you to remember for now. All right. I'm going to pause here. How are we doing? So far, so good? Okay. I do want to look at one more problem on units, and then we'll take a 10-minute break, and then we'll come back and do the group activity to close out the day, okay? So I got to give you a break once in a while. So let me see if I could just look at one more problem here. We actually have some really good notes for this stuff. Okay, this one. I want to point out physics problem 1.33. So notice I say blatantly follow the solution. I'm going to try and show you how to do units math. But for me, there's a thing called dimensional analysis. Okay. Your textbook does a bad job at this. So I want to show you a write-up that's in the, whoops, not this one. I went to my own live stream. How meta. All right, that was earlier, trying to test it, make sure it works. Let's go to here. Sorry, let me show you something. Thanks for your patience. Let's get rid of it. Oh, Zoom. Okay, somewhere in here. This is the group activity. So right after we come back from the break, this will be how you do the group activity. Here's a link to the concept warehouse. If you're having trouble with that, we could talk about this. Here it is. Supplement covering dimensional analysis. If you click on this link, it should open in a new window. And so this walks you through a lot of the dimensional stuff that your textbook is bad at. So Vince Tobin wrote this, and it's really awesome. And he goes through all this stuff. He talks about what all these symbols mean, and your textbook does not. Okay. So I'm going to let you read that on your own after class, but I did want to point out where that is. Oh my gosh, it's so slow. Okay, so it's somewhere in week 1 in the lecture readings. There's this tip for how to do dimensional analysis. All right, but so that said, let me just do one quick example here. Let me just make one up. Okay. All right, so you know problem 33, just stare at the solutions and use it. You've got that extra handout, but here's an example just to see if you know what you're doing. Let's say we say x equals a k v t. How about kv over t minus b a t. All right. So let's say we have an equation like this. The units of, this is how I write the units of x. Typically, when you see a letter X in a physics class, it has units of meters. Sometimes you'll see people write it like this, or just a capital L sometimes, but I just generally use meters. So notice M is different from the units of M, okay? Anyways, let's say the units of V, those are typically meters per second. The units of T are usually seconds. The units of A are usually meters per second squared. So notice this is not saying velocity is meters per second squared. It's saying the units of velocity are meters per second. Sorry. The units of velocity are meters per second. The units of acceleration are meters per second squared. And time has units of seconds. So when we do these goofy square brackets, that's what allows you to write the units without the number that's supposed to go with it. Okay. So if I look at this thing, let's say I ask you, what are the units of K? Here's what I want you to think. I know that the units of this thing are meters, right? The units of X are meters. So what do the units of this entire blob have to be?
Meters.
Meters. What do the units of this entire blob have to be?
Meters.
Meters. This equation will only make sense if we're doing apples equals apples plus apples, right? You could only add apples to apples, or in this case, meters to meters. If you want to have meters for your answer, each term has to be in meters, and that saves us a lot of work. So here's what we do. We say, okay, the units of X have to equal the units of K times the units of V over the units of time. Rather than solving for K algebraically, we solve for the units of K algebraically, knowing that each separate term has to be of the correct unit. And that saves us so much work dealing with this junk. Well, now I'm just going to flip this around and say that the units of K should equal the units of X times time divided by V. And again, I mean units of time and units of V. So now it's easy. It's meters. Whoops. This is going to be X is in units of meters. T is in units of seconds. And this one is in units of meters per second. Notice I do not draw the diagonal fraction bar. Why? Because it gets confusing. So now what do? I get this out of the denominator by multiplying by seconds over meter on the bottom and the top. What happens on the bottom? Seconds cancel, meters cancel. On the top, meters cancel. And it looks like this has units of seconds squared. You could do something similar to figure out the units of that constant b. All right. Let's take a break.